FIFO page replacement. This is the simplest page replacement algorithm. FIFO stands for first in, first out. So the oldest page will be chosen to be replaced. This will be the victim page. For that, we can assign a time, when the page is bought. And it is not strictly necessary to assign a time to know which one is oldest. We can use simply a queue. So the latest will be put in the tail, and in the head will be the oldest. So we will delete, or you can say we will use it as a victim frame, and we'll put or take this page out from this queue, and then we'll place it in the backing store. Quite easy to understand and implement. As you see here, we have a reference string. These are, say, the pages. We have 3 frames. So these 3 pages can be in memory at a time per process. So we have 3 frames here, 1, 2, 3. If this comes 1, 2, 3, so 1 will be placed here, 2 will be placed here, 3 will be placed here, because there is no page inside this frame. So there will be 3 page faults. Then 4 will come. Oldest one is 1. So we have to replace this 1 by 4. Okay, this will be replaced. Now 1 will come because we have just replaced this 4, and this is the newest one. We have to replace this 2 with this 1. Now in this 3, we have 4, 1, and now 3. Okay, now 2 will come. So we have to replace now this 3 with 2. Then 5 has come. And in this 4, 1, 2, the oldest is now 4. So we replace now this 4. Right? 4 with 5. So 5 will come here. Now 1 will come again. And 1 will come. Again we can see that what will happen. We have to replace which one? Since 5 has just come and 3 and 4 is there, but this 4 is being here for quite a time, and this 1, as you see here, 1 has come now, but 4 has come before. So we have to replace this one, right? So in this way we can replace all these strings. So in all there will be 9 page fault. But there is also a possibility we can increase the frame number. If we increase the frame number and we perform the same activity, that is first in, first out, then we see the page, because of increasing the frames, the page fault will increase. I'll show you with a proper example. If this is a string, see, 7 will come, 7 will go here. 0 will come, 0 will go here. 1 will come, 1 will go here. So 3 page faults. All these blue bars show the page fault. Now 2 has come, which has to be replaced. This 7 has to be replaced. This is the oldest one. 2 will come here. 0 already there, so there will be no page fault. 3. Now 3 has to replace which one? Because 0 is now the oldest, 3 will replace this 0. Now 0 has come. 1 is the oldest now, so 0 will replace this 1. Then 4 has come, which has to be replaced. 2 is the oldest, so 2 will be replaced by this 4. Again, now 2 has come. 2 will be replacing this 3 because this is now the oldest. 3 will come. 3 has come, but 0 is now the oldest, so 3 will go here. 0 has come. 0 will, this 4 is the oldest one. 0 will take this place. Since 3, 2 is already there, there will be no page fault here. 1 will come. 1 will replace this 2. Right? Then 2 will come. 2 will replace this 3. So 2 will come here. Now 0 and 1 is there. There will be no page fault. 7 will come. 7 will come here. So 0 has to be replaced. Now 0 has come. 0 has to replace 1. 1 has come. 1 has to replace this 2, because all these which are oldest or out of 3 will be replaced. So there are 15 page faults. So there is a B-lady anomaly. Now B-lady anomaly is when you increase the frame size. If you increase the frame size, this is obvious that the page fault should decrease, but this is not the case. Just see this illustration. When we increase the number of frames, here the number of page fault has increased. This is the number of page frame 3, and this is 4, so it has increased. This is called the B-lady anomaly. Now we come to optimal page replacement. This optimal page replacement, because we had B-lady's anomaly in FIFO, as we increased the frame, the page fault increased. So the optimal page replacement, it guarantees the lowest possible page fault rate if we have a fixed number of frames. And this algorithm exists and it is either optimal, OPT, or minimal, right? But there is a difficulty. This algorithm says we need to have a future knowledge. How to have a future knowledge? Because this is very difficult to implement, because future knowledge of the reference string or the pages is very difficult and mainly used in these comparative studies. The algorithm says replace the page that will not be used for the longest time. So you will see when we see an example, there are so many criterias, criterias can be combined to find the victim page or victim frame, right? So this is quite difficult, but still we'll try. This is a frame. See, there are 4 frames in all, and this string has come. So we try to replace, and there are 6 page fault. So how to know which to replace? This is the question here. There are so many, as I just said, this is used to measure how well your algorithm performs, because this is optimal. Why it is difficult? Why it is difficult to implement? Because of future knowledge. Which knowledge you will use to replace? So the optimal page replacement, let us take an example, just combining some criteria so that we understand the future knowledge. See, I'm just giving you an example. 7 has come, 0 has come, 1 has come. So there will be page fault, no problem with that. Now 2, as we said, 7 is there for a long time, let us replace 2. 0 is already there, now 3. Because 0 is just referenced, don't replace it. Put it 3, replace 1. Now 0 has come, 0 is already there, now 4 has come, now replace the 0. Put 4 here. 2 and 3 is already there, there will be no page replacement, or there will be no problem. But 0 has come. So now replace this 4. Because 2 and 3 has just been referenced, so we will not replace this 2 and 3. We will replace this 4 with 0. Now again this 3 has come, 2 has come, now 1 has come. So 1 has to find its place. So 3 was referenced earlier, that is why we replace this 1 with the 3. Then 0, 1 already there, now 7. 7, as we just saw, that this 0 and 1 has just been referenced. 2 was not been referenced, it was earlier. So we replace this 2 by 7. This is how we can use some future knowledge to implement the optimal page replacement. But here we have very good result, that we have just 9 page fault. If you do with the FIFO algorithm, you will get 15 page faults. We have LRU, least recently used page replacement. This is just an approximation of optimal page replacement algorithm, because optimal page replacement algorithm is quite difficult to implement because of the future knowledge, how to anticipate what is going to happen in future. So we use the recent past as an approximation of the new future. We just replace that page that has not been used for the longest period of time. Just take optimal page replacement and think backward. What we'll do here is, if this is a reference string, see, 1 will come here, 2 will come here, 3 will come here, and 4 will come here. There will be 4 page fault because initially the frame will be free. Now see, now the 1 will come, so there will be no problem. 1 is already there, 2 is already there. Now 5 has come. What this 5 will do, this will replace 3, because 3 was not being referenced. 3 was not being referenced for quite a long time. So now this 5 will replace this 3. Now 1, 2 has come, 1 and 2 are already there. Then 3 will come. So 3 will replace, this 4 will replace, or 3 is going to replace 4, because 4 again was being replaced or was being referenced quite earlier, before 1, 2 and 5. So we are not able to, or will not replace 1 to 5, will replace this 4 with 3. Now again this 3 has taken place, now 4 will come. Again we see 5 was 1, 2, 3 was referenced just now, 5 was referenced earlier, so we'll replace 4 with 5. Now again 5 has come, because 1 was referenced earlier, it was not recently used, so we'll replace now 5. This is how it is done. We'll take one more example. This is 7. 7 will come, 0 will come, 1 will come. Now which is the oldest? This 7, not being referenced just now. So we replace this 2. Now this 0 has come, it is just being referenced, now 3 will come. So we have to replace, 0 has just been referenced and 2 has come early, just now, before 0. But this 1 was earlier than 2 and 0. So 3 will replace 1. This will be replaced. 0 is already there. 4 will come. 4 will replace what? 2, because it was earlier. It was least recently used. 4 will replace this. 2 is already, then 2 will come. 2 will replace 3 this. Okay, because 3 was quite earlier. Then next, if 3 comes after 2, we have to replace this 0. This 3 will replace. Then 0 will come, we will replace this 4. Now 3 and 2 is already there. Now 1 has come. 1 has to replace, 1 will be replaced by 0, because 0 was quite earlier than 3 and 2. So this is the case. Now 2 has come. Since 2 is already there, will not replace. Now 0 has come. We have to replace 3. It was quite earlier. 3 will be replaced. 0 will come here. Now 1 is already there. Now 7 has to be seen where we have to put. 2 was earlier than 0 and 1, least recently used. So we will replace this 2 with 7. How many page fault? 12 page faults here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Number of bars you can count. So there are two ways to determine the order of frame, defined by the time of last use. Because in least recently used, how we know that which one is least recently used? We can use a counter, we can use stack. So in counter, each page table entry has a time of use field, right? In page table only we'll put the time, and the CPU gets a logical clock or counter, so that we may be knowing which is least recently used. So whenever a page is referenced, the content of this clock or this clock register are copied to the time of use field in this table and in the page entry table for that page. If you want to see the stack version, whenever a page is referenced, it is removed from the stack and put out on the top. Removed and put it on the top. So the bottom one will be the page which has to be, which is the victim, which has to be removed. So this is how it is done. This is stack. So this is stack after B. We can use this. So whenever this is referenced, say 4 is referenced, then 7, then 0, then 7 has again come. When 7 has come, we have to take it, means you have to swap it out, or you can say in terms of stack, we do push and pop. So we will pop out and put it on this 7. This is recently used. This is how it is done. So neither this optimal replacement nor this LRU replacement suffers the Bill-Eddy anomaly. This LRU approximation page replacement, you can have a reference bit also for LRU. We can just associate a bit with each page. Initially make it 0. Whenever the page is referenced, the bit, this 0 we will change it to 1 by the hardware, and replace the 1 with 0 if at all it exists. We do not know the order. We have additional reference bit algorithm. See how it helps us. You can get some additional ordering information by recording the reference bit, but now at regular intervals. So we'll use a 8-byte. You can have a 8-byte. This is used for each page in table in memory. So this is actually a register. So this register is a write shift register. Say for this regular interval, let us take 100 millisecond. Every 100 millisecond the page are referenced, and if the page was used, then a 1 is moved into the most significant bit of the byte. This is the most significant bit. See, this 0000 8 times means the page has not been used in last 8 times unit. That is 8 into 100. 8 into 100, that is 800 millisecond. How about 111111 8 times? This page has been used every time in the last 8 time units. How about this? See, this one's just being used. This was not being used. So this is more recent than this. So this can be treated as, say, unsigned integer, and the page with the lowest value in the LRU of this bit unit can be used. If both of these are equal, then we use the first come first serve. We have one more thing which is called as the second chance algorithm. So like the FIFO replacement algorithm, this is just like FIFO replacement algorithm, first come first out or first in first out. But here we inspect the reference bit, and now we replace the page if the value is 0. If the reference bit is 1, then that page gets a second chance. See, if the reference bit is 1, we'll give it another chance. So its reference bit is cleared, it will make it 0, and its arrival time is again reset. So it gets another chance. So the page that has been given a second chance will not be replaced. It will not be replaced until all other pages are replaced. This is second chance algorithm. So if the page is used often enough to keep its reference bit set, it will never be replaced. It will never be replaced. This second chance is you need a reference bit, as I just indicated you. We have a clock replacement. If the page to be replaced has reference bit 1, then we set the reference bit to 0. We leave the page in the memory and we replace the next page which is in the clock order subject to the same rules. This is a second chance, and this simply shows that we give a chance if it is 1, reset the values, and we just give it another chance so that others let other complete, and then this should work. We have enhanced second chance algorithm. Here what we can do, we can consider both the reference bit and modify bit as an ordered pair. Ordered pair means this 0 0, this simply means this is neither recently used nor modified. This one is the best to replace. The 0 and 1 means that it is not recently used but it is modified, not quite good as to this one. And 1 0 means this is recently used, one is recently used but it is clean, and that will be used again probably. 1 1 means it is recently used and it is being modified, so this probably this will be used again, and this will need to be returned to the disk before we can replace it. We also have counting based page replacement. We keep a track of counter of number of reference to each page. We can have LFU and MFU. LFU says least frequently used, MFU says most frequently used. So this LFU page replacement algorithm, the page with the smallest count will be replaced. In the MFU most frequently used, the page with the smallest count was probably just being bought and it was not being used. We also have page buffering algorithm. See, if the page is read into a free frame from the pool before a victim frame is written out, the page is to read into free frame before we can get a victim frame. So the process can restart as soon as possible without waiting. So the buffering is just because to decrease or to avoid this waiting time. So without waiting for the victim page to be written out. Okay. So whenever the page device is idle, not doing any work, so the modified page is selected and returned to the disk, increasing the probability that the page will be clean when selected for actual replacement. So you can remember which page was in each frame for the pool and reuse the old page directly if needed, before the frame is reused, of course. So the application page replacement, see, if you talk about databases, these are the application processing, data. They know better. These databases knows better how to handle their own data than the general purpose use of page replacement used by operating system. Sometimes it is better that let database handle it. The data warehouses, they perform massively, they are a huge sequential disk read, and this is followed by quite a computation and writes. So this MFU becomes quite efficient than the LFU in this case. So how to allocate the frames? Each process need some minimum number of pages. For example, if you take IBM 370, it has 6 pages. It needs 6 pages to handle the move instruction. So instruction here is 6 byte, and it might go to 2 pages. So 2 pages to be handled from and to, right? So there are major allocation scheme like the fixed allocation, priority allocation, and the minimum number of frames. See, the instruction set architecture, it defines the minimum number of frames that can be allocated. Because we need to know how many frames has to be allocated. The maximum number is defined by the amount of available memory. The algorithm for allocation can be equal allocation or proportional allocation. That is, equal allocation means just allow or give every process equal frames. In proportional allocation, allocate memory to each process according to the size of the size. See, what size the process is, allocate accordingly. So we can have a global as well as local allocation. Global replacement, you can say a local replacement. Global replacement means a process can select a replacement from whole set, all the available set. So now the process may, here the local replacement, the process select only from its own set, of allocated frames. So in this global replacement, a process may even select only frames allocated to other process. This will increase the number of frames allocated to it. But the problem here is the process can't control its own page fault rate. This global replacement is quite a common method, since the throughput is quite high. And in this local replacement, the number of frames allocated to a process, it does not change because it is local, it is already been assigned. Then we have thrashing. What is thrashing? If a process has not enough pages, then what to do? That means if the process does not have enough pages, there will be page fault. Page fault will be quite high, and when the page fault is high, the process will be doing more of the work in, swapping out, or doing the page fault, handling the page fault. There will be low CPU utilization. The operating system thinks that, okay, the degree of multi-programming is getting higher. But the thing is that the CPU utilization is low. There is another, if the number of frames allocated to a low priority process falls below the minimum number required, it may be suspended. So let me tell you thrashing again. A process of thrashing, or you say a process is thrashed if it is spending more time paging than actual executing. See, the system will see that all pages are in use. It will see a lot of multi-programming is going on. But the thing is that it is actually replacing and putting forth, in and out. So this is thrashing. What is the cause of thrashing? The thrashing is when we have no enough pages. So a process will keep faulting. They queue up for paging device, so the CPU utilization will decrease. A CPU scheduler sees the decreasing CPU utilization and will increase the degree of multi-programming as a result. And the new process will even cause more page fault, right? See, this thrashing is, we have degree of multi-programming you want to increase. This is CPU utilization. When you increase the degree of programming, you see at this point, degree of multi-programming is of course increasing, but the CPU utilization is being decreased. This is thrashing. This portion is under thrashing. So we can limit the effect of thrashing. How? By using the local replacement algorithm. If a process starts thrashing, if we are able to understand and know that if a process is thrashing and it cannot steal the frames from other, we can the pages are replaced with regard to the process of which they are part. You cannot take from other process, right? So we can the effective access time will also increase. So in order to prevent this thrashing, the one obvious idea is to give more frames, right? So again, if you allow more frames, then there will be again certain comprehensions. We can use the working set model. What this working set model shows is, as we just saw, the page which is being used or which is just now used, it will be used again, and the pages which are nearby will always be used, will also be used. This is an idea of locality. So working set model, this is based on assumption of locality. I'll show you how. This is what is done. See, this page from here to here, we take a delta, a time. So all these from 2 to 1, if this is delta, for this delta time, all these pages are kept in this working set model. From here to here, see, we have kept 3 and 4 because only 3 and 4 are referenced. These are kept in this working set model. So what I'm trying to suggest here is, this is based on the assumption of locality, as you just saw. So we have a parameter delta, which is actually the time, which defines the working set windows. So working set will have what? It will contain the set of pages which are most recently used in that delta time. So if the page is in use, it will be in working set. Otherwise, after delta time, we will drop it from the working set. It will not remain in working set. So the accuracy of working set depends totally on the delta you have chosen. If delta is too small, it will not encompass the locality properly. If delta is too large, there will be some overlapping between different localities, right? So this working set strategy, it prevents thrashing. It will prevent thrashing properly while keeping the degree of multi-programming as high as possible. So this is one of the solutions to avoid the thrashing. So I'll show you how it is done. First of all, say we have a delta which is the working set window. This is the fixed number of page references. Say we have 10,000 instruction. So this WS, the working set of process PI, this is the total number of page which is been referenced at this time, from here to here, from here to here. So these are the working set. These are set actually. So if delta, as we said, too small, no locality, large, we have some say we have some overlapping. So what we will do here is we take D, which is the sum of all these working set, all this sum of the working set, and this is the total demand frames. If this demand frames is greater than M, which is required, this is what is required, and it is greater than a page requires more frames and it is not getting it, so there will be thrashing. So what is the best criteria? The policy is, if a process it has something like this, if the working set summation is greater than what is being assigned, we just suspend that process. We have page fault frequency, that is, this is quite a direct approach than the working set model we have just seen. In order to prevent thrashing, we control the page fault rate. When it is too high, we know the process needs more frame. So when it is too low, we know the process has too many frames. We know. If it is thrashing, that means it has less frames. If it is not thrashing, that means it has too many frames. So now what we do here is we assign an upper and lower bound for the desired page fault rate. So we allocate and remove frames accordingly. I'll show you how. This is the page fault rate, this is the upper bound, this is the lower bound. These are the number of frames. From here to here, if it goes up above this upper bound, we increase the number of pages. If it goes below this line or this lower bound, we decrease the number of page. Or what we will do here is, if the page fault rate increases and we have no frames which are available, then we will select a page, we'll suspend it, and whatever frame it has, we will redistribute it to others. This is what we'll do. So this is all about this very important memory management virtual memory concept. Thank you so much. Take care of yourself.